Folks, good morning. Any questions? Okay, so just a reminder, we are going to have our quiz number 6, I believe, on Tuesday, and the topics to be covered are anything that appears in this chapter 8 that we have covered in class, the inverter concept. What we did first was we looked at single-phase inverters, a topology like this. It's like an H-bridge kind of a thing. First switching scheme was a square-shaped switching scheme that gave us an output voltage which was a square shape, like this. And we try to find a steady state response of the current in case we have a load which is comprised of a resistor placed in series with a capacitor and inductor, and it turned out to be like an exponential kind of term like this. Then we looked at switch realization. I mean, those ideal switches that we had turns out to be they have to be implemented with, for instance here, one IGBT with a diode that is in anti-parallel with that IGBT, or a MOSFET, because MOSFETs already have this internal diode that can act like this anti-parallel diode, because the reason that we need this diode is sometimes this current is negative and for instance IGBT may not be able to handle that current, so you need a diode to do that. Then we looked at introducing some negative, some zero values or dead values or dead bands to your square-shaped waveform, and the advantage over here is by introducing this angle of alpha, you can control the amplitude of the fundamental harmonic that you are generating. So if you increase alpha, so for instance, if this is the amplitude of my fundamental harmonic, if I increase alpha, it's going to get smaller. So basically you can argue that by adjusting the value of alpha, you can control the amount of power that is being delivered to the load. Then there is a simpler version of this H-bridge inverter, which is, it doesn't have 4 switches, it only has 2 switches, but then we are splitting the input voltage waveform to 2 halves using 2 relatively large caps. And again, if you do everything symmetrically, the average value of this current should be 0, and it will be 0, therefore you don't have to worry about the voltage of these caps getting out of where they are supposed to be. They are usually half of the DC voltage. Then we briefly kind of introduced this concept of if one H-bridge does not work for you in terms of the total harmonic distortion being very high, you can actually put a bunch of them in series with each other or cascade them and construct voltages that are like a stair-shaped. And the argument over here is you have better resolution on the y-axis, therefore your total harmonic distortion is better. Also, you have 2 degrees of freedom in terms of selecting alpha 1 and alpha 2. They could be, for instance, used to eliminate a particular harmonic in the voltage, for instance, the third harmonic. Then you can keep doing that and keep stacking these H-bridges with each other. Like, for instance, you want to achieve a high voltage value using a low voltage DC sources that you have available, and construct an output voltage that is, again, a stair-shaped, a staircase kind of a thing. But again, the argument is you are getting closer and closer to an ideal sinusoidal waveform as your output voltage. Then there are other ways of doing that, this is the whole concept of multi-level converters, or in this case, multi-level inverters. We actually talk in details on this about these topologies in the course WE3 453 Advanced Power Electronics. Okay, now then, still on the single-phase topologies, we introduced the PWM switching scheme. And the difference over here is now we are making decisions on what switch should be turned on or off based on the comparison that we make between a sinusoidal signal, which is kind of our reference, which is this guy over here, and a relatively higher frequency triangular waveform, which is called a carrier signal, which is this guy. And the frequency of these two signals, the ratio between them is called MF, which is the frequency modulation index, and the amplitude ratio is MA, which is the amplitude modulation index. MF is usually an odd number, like, I don't know, 17 or 15 or something like that. One thing that I haven't mentioned in this class, what's actually important to remember is, in terms of phase, whenever your reference is going from negative to positive, like at this point over here, your triangular waveform is actually going to the negative areas. So remember that. So if you, let me see if I can pick a different color here. So if you do it this way, you are probably going to get into some troubles. So let's say this is your carrier, and this is your triangular. Okay, so in terms of the phase thing between your triangular and your sinusoidal, whenever you are crossing zero, like over here, your triangular first go to the negative areas, then goes to the positive areas. So just keep that in mind in case you're implementing this, because you may actually face some troubles. There are many PWM switching schemes. The two simplest one that we kind of talked about was, the first one was the bipolar one, and the reason that it is called bipolar because in each half cycle we have both positive and negative polarities. And then you have a unipolar switching scheme. The logic is a little bit different, but in the end the output voltage in one of the half of the cycles is either positive is 0, and in the other cycle it's either 0 or negative. Then we looked at the frequency spectrum of these signals. Like this particular one is the bipolar PWM. And remember, most of the times these numbers are normalized by the DC value of your source. The other thing that you have to remember is, are these values giving me the amplitude of the signal or the RMS value of the signal? So far, these tables that we have had, they give you the amplitude of the signal. So you can see that, for instance, if you choose, I don't know, an amplitude modulation index of 0.6, you have a fundamental harmonic at the amplitude of 60% of your DC source. Then at MF, for instance, 15 or 17 or whatever it is, you have about 101% of the DC source. Then at 15 plus or minus 2, these are the sidebands, you have about 13%. So it's actually describing what is happening over here. So the main advantage of the PWM signal is these harmonics are kind of apart from each other, so it's easier to filter the undesired harmonics. This particular table is almost the same thing for the unipolar switching scheme. And we looked at some simulation results from these slides. And we started talking about three-phase inverters. And the reason that we want to do three-phase is a lot of times when your power is high, it's better to do things in a three-phase fashion. For instance, if you have, I don't know, 10 kilowatts of a, for instance, fuel cell generator and you want to send power back to the grid, you better do it in three-phase. And in addition to that, a lot of times our electric motors are three-phase electric motors. For instance, let's say you have a hybrid or plug-in hybrid electric vehicle, and the electric motor that you have is a permanent magnet synchronous machine, and it's a three-phase machine. So you basically need to have a three-phase inverter for that. The topology is something like this. You have basically three legs. Let's call this leg A, leg B, and leg C. And each leg is comprised of two switches. So basically, if you really want to physically realize the switches, these are all IGBTs, anti-parallel with a diode. So I have the same thing over here as well. Obviously, switches 1 and 4 are not supposed to be on together, because if you turn both of them on, you're shorting your source. And they are not supposed to be off together at the same time either. Why is that? Because this current is usually a continuous current. So it should basically, there's usually an inductor somewhere around here which forces the continuity of the current. So if you turn both of these switches off, what happens is this current has no place to flow through and something bad may happen, and that's actually what the diodes take care of. Whenever you turn the switches off, the diodes are going to be on, so there's always a conduction path. But if you really look at, leg A, what you see is basically a single pole double through switch. So when switch number 1 is on, that means point A is shorted to this point, which is the positive terminal of your source. When switch 4 is on, point A is actually shorted to the negative terminal of your source. So it's basically you have a single pole double through switch. Sometimes you are in this, like a light switch. Sometimes you are in this position, or you are in this position. You either pick from the DC of 100, VDC, whatever that value is, or you pick from 0, something like that, assuming that this is the ground. And the load is a 3-phase symmetric load. Makes life much easier to analyze those loads first. And in this particular case, we are focusing on Y-connected loads. So what we did last time was we looked at the very basic switching scheme. It's not PWM yet. It's not high frequency yet. It's called a 6-step inverter, or like a square-shaped kind of inverter. So basically what you do is you divide your period into 6 equal intervals, like this. So this is my period. And for instance, when it comes to S1, you keep S1 on for the half of the period and then off or open for the remaining half of the period. Then when it comes to S2, you do the exact same thing with 1/6 of a period of phase lag, phase delay. So this is basically the same thing, only delayed. So if you actually look at this diagonal line, you can see that you're basically doing the same thing, only with delays. So S2 is delayed from S1 and S3 is delayed from S2. And please remember the order or the way you're numbering the switches is important. S1 is here, S2 is down here, S3 is up here, S4 is here, and then 5, and then 6. So this order really matters. So in the end, if you look at, for instance, your okay, we are labeling this to be point A, point B, point C, and N is the neutral point of the load. And please remember, this has nothing to do with the ground. So the neutral point of your load is not your ground. They're totally different, basically, nodes. VAB, which is like a line-to-line voltage, turns out to be a square shape like this. And VBC and VCA are the same. There's only 120 degrees of phase shift between them. So basically, you can see this waveform is just moved to the right as time goes on, and you go from phase A to phase B to phase C. If you look at VAN, which is basically the voltage of point A with respect to the neutral point of the load, it is again like a staircase kind of a waveform. It looks like this, and the levels are, this level is 2 VDC or 2 VN over 3, and this level is VN over 3. And it's totally symmetric, so the negative values are actually the same, just negative 2 VN over 3 or negative VN over 3. And again, VBN and CN are the same. They are only phase shifted, so you can actually argue that everything is kind of phase shifted with 120 degrees, which is what we expect to see in a 3-phase system. We didn't really look at the current waveform, but imagine that this converter is connected to a load, and on each leg of this load we have an inductor, and in series, like for instance the winding of a motor would behave like this, and then your current waveform is going to look like this if you do the simulations. You can see it's not really triangular, it's not really sinusoidal, but you can argue that there is a relatively large AC component in this current. And there is a phase shift between the current and the voltage, which is an indication that, well, obviously this phase shift is like the current is behind the voltage, therefore that means there is some sort of an inductor in the winding. And that's usually almost the case. We also looked at the Fourier series analysis of this particular converter. So N is highlighting the order of your harmonic, like 1, 5, 7, and stuff like that. And L to L means line to line. So basically we are looking at, for instance, VAB over here, or VBC, or VCA. And okay, these two waveforms, hold on, this second one should be V line to neutral, I guess. Let me check. Yeah, I guess there's a mistake over here. This should be line to neutral. And when it comes to order of harmonics, you're looking at a fundamental harmonic. We don't have any even harmonics because everything is symmetric. You may have odd harmonics. However, because this is a three-phase system, all of the multiplies of 3 are all eliminated. So you don't have a third harmonic or a sixth harmonic and things like that. So technically, you have the fundamental harmonic, then you have the fifth harmonic, then seventh harmonic, then 11th harmonic, then 13th harmonic. So if you look at this is like yeah, actually, let me see. What did I do that? 6K, yeah, 6K plus or minus 1. So if K is 1, it gives you 5 and 7. If K is 2, it gives you 11 and 13, and you can go to higher, actually, harmonics. So in case you are interested in the RMS value of a particular component or the total harmonic distortion, things like that, you can actually use these equations and get the numbers that you need. All right. So far was the review. Now what we are going to talk about today is three-phase inverters, PWM switching scheme. So let's talk about that. Do we have any questions so far? All right, no questions. So let's move to our OneNote thing. Okay. So the three-phase PWM is almost the same as the single-phase PWM. You still have one triangular waveform, but now because you have 3 legs and you are supposed to generate basically 3 voltage signals, VA and VB and VC, therefore you have 3 references, 3 sinusoidal signals. So as you can see over here, I have this reference which constructs, for instance, phase A for me. So this is reference for phase A, and you can see it says VA reference, obviously. Then you have phase B reference, which is, because it's a 3-phase system, 120 degrees behind phase A. And obviously it says phase B reference. And then you have, let me use, this is already black, but anyway, let me use phase, don't have a lot of options here. Here, let me use yellow. Although yellow doesn't look very good. But anyway, it is phase C, which is 120 degrees behind phase B, and phase B was 120 degrees behind phase A. So you have these 3 symmetric sinusoidal signals generated. Obviously, the amplitude of these signals is variable. Depending on how much voltage in terms of amplitude you want, you can actually adjust the amplitude of this signal. The frequency of these signals could also be variable depending on, do you want to have a constant frequency or variable frequency kind of an output voltage. Although most of the times you don't really mess around with the frequency. Again, because of some symmetry stuff in the system, please remember that when it comes to the phase angle between your reference and your triangular waveform, remember whenever phase A is crossing 0, going from a negative value to a positive value, your triangular waveform first goes to the negative area, then comes to the positive area. All right. And we kind of want to do the same thing for other phases. You can see that for phase B, almost the same thing happens. Whenever your phase B reference is going from a negative value to a positive value, your triangular goes to negative first, then comes up to positive. And also for phase C, you can focus here and make the same argument over here. So it's kind of an indication that when it comes to selecting MF, remember MF was the ratio between the frequency of this triangular to the frequency of our reference. MF should be an odd number. And we see why. Last time I had that mathcat file, and I choose intentionally and chose an MF of, for instance, 18, and it actually gave me a lot of lower order harmonics, like harmonics at n equal to 4 and stuff like that. So for that reason, we choose MF to be an odd number. The other one is relatively large. For instance, an MF of 3 is not acceptable, or MF of maybe 5 is not acceptable. It's like 15 or something like that. And because we want to do this, that with respect to phase B and C and A and B and C, it have some sort of a symmetry. It has to be a multiple of 3. So for instance, MF could be 15, for instance, okay? Then, I don't know, 21 maybe, 27. You know, these numbers are good values to choose MF from. All right. The rest is the same. When you focus on phase A, you only care about what's happening between your triangular waveform and the reference that you have generated for phase A. And by the way, when you want to implement this system, you can use DSPs, digital signal processors, and they already have everything that you need. They generate these triangular waveforms, they generate these references. You don't really have to worry about anything. So for instance, when it comes to phase A switching, what I do is I compare this reference with the reference for phase A and the triangular waveform whenever the reference is, I honestly don't know if this is drawn correctly or not. I don't think these are the right scale, but anyway, we do almost the same logic, and we end up having a waveform like this for what we generate at point A with respect to the ground. So basically, I'm talking about this voltage over here. The voltage of this node with respect to the ground. Okay, whenever it comes to generating or synthesizing this voltage, then we make a comparison between the reference for this phase and the triangular waveform, and we do almost the same thing for phase C. So in the end, you have actually these kind of, in this graph, only 2 of them are drawn. These 3 kind of PWM signals, and you can see phase B is like 120 degrees behind phase A. There is no phase C drawing, but that would be 120 degrees behind phase B. So when you have VA with respect to the ground and VB with respect to the ground, when it comes to the voltage of A with respect to B, or VA with respect to the ground minus VB with respect to the ground, so I just get a subtraction between these 2 signals, and that gives us a kind of a line-to-line voltage waveform, which is kind of the PWM, similar to the PWM signals that we saw for the single phase case. It doesn't look like sinusoidal, but there is a large fundamental harmonic in it. Then you actually see a graph over here down, which is VAN. So we are looking at the voltage of node A with respect to this neutral point of the load. So this would be VAN. So it's like a line to neutral kind of a voltage in a 3-phase system. We had equations last time for it. Technically, once you find VA with respect to the ground, and VB with respect to the ground, and VC with respect to the ground, VA with respect to the neutral point would be twice VA minus VB minus VC over 3. And you can do the same thing for other phases. You can see voltage of node B with respect to the neutral point of the load would be twice V. And you can do the same thing for phase C. So if you do the math, then you end up having a voltage waveform like what you see over here. So this is the line to neutral voltage of this PWM bipolar switching scheme for phase A. And then you can divide this voltage waveform by your impedance or whatever your load you have, or do some circuit analysis and find out that your current waveform is something like this, depending on what kind of your load you have, and most of the times your load is a resistor placed in series with an inductor. All right, so it's kind of like the single phase thing. We're just doing things 3 times and with 120 degrees of phase shift from each other associated with the 3 phases. Now, what people have done, and it's very useful to use, is they have looked at the harmonic content of the voltage signals that are generated. For instance, they have looked at this line-to-line voltage and have tried to calculate the harmonics of this line-to-line voltage. And the results of those are reflected in tables. So like this. This table does not come from your book. It comes from another book by Dr. Ned Mohan, but it is posted on Blackboard, so if you're interested, you can take a look. It's called a 3-phase table. And when it comes to these tables, you really have to be careful which one is the right one to choose and what kind of numbers it is actually spitting out. So let's take a look. First of all, it doesn't say anything. Let me see. It doesn't say anything, but remember, this is for a 3-phase bipolar switching scheme. All right, so that's one thing to remember. The other thing is the number that you see here are reflecting the magnitude of the line-to-line voltages, not line-to-neutral voltages. Line-to-line voltages are like VAB, VBC, things like that. VAB, VBC, or VCA. All right? And again, the assumption is MF is an odd number. It's large, and it's a multiple of 3, and we already argued why. So odd, large, and a multiple of 3, for instance 15 or 21 or something like that. And the other thing that is very, very, very important, if you look at down here, is first of all, these numbers are normalized by the input source. So if you see a number 1, that means 100% of the DC source that you're using, okay? So remember, we have a DC source here. Okay, so it's like 100% of the value of this DC source. The other thing that is even more important is this particular table is giving you the RMS values, not the peak values. So far, all the tables that we have had, they are giving you the peak values. This particular one, I don't know why, it is giving you the RMS value. So it's very, very important to keep that in mind. So this is one table. So the suggestions are, like on this axis, we have MA, the amplitude modulation index, growing from 0.2 all the way to 1, covering the entire linear region. We only have steps of 0.2, 0.4, 0.6, 0.8, and 1. For instance, for 0.3, we don't have anything. Well, there's another table down here which actually gives us some values for 0.3, but if you don't have access, what you can do is, which is a kind of an approximation, is just take the average of these 2 numbers. And that gives you a rough estimate of what your harmonics are at 0.3. And you can see where our harmonics appear at n equals 1, which is the fundamental harmonic. Then n equals, we don't have harmonic at n equals mf, but we have some side bands at n equals mf plus or minus 2. And then plus or minus 4, and then 2mf plus or minus 1, and so on and so forth. So we have all of these harmonics. And the good news is, if you look at this box, unlike the single phase approach, you don't really see a very large number in this box. That means all of the higher order harmonics are small to begin with, and they happen at higher frequencies, so it's very easy to get rid of them. All right, so this was one table, and this other table, which is actually in your book, table 8.8, chapter 8, table number 8 of your textbook, and it almost gives you the same values. So again, it's highlighting that this is for a three-phase PWM. All of the voltages are line to line. It still doesn't tell you that this is for a bipolar three-phase system. And this gives you the amplitudes, not the RMS values. So basically these two tables are similar. However, the difference is you don't see any numbers identical because, for instance, let me make this a little smaller. So technically, if you divide 0.866 by the square root of 2, you should basically get this number. So these numbers are the same. There is the differences. Division by the square root of 2. Well, obviously because one of them is giving you the amplitudes, the other one is giving you the RMS values. But again, all of these are line-to-line voltages. If you happen to want to do line to neutral, remember line to neutral is 1 over the square root of 3 times the line-to-line voltages. The good thing about this table is it actually gives us a better resolution for MA, 0.1, 0.2, all the way to 1. It's the other way around. Instead of increasing, it's decreasing. But in terms of depth of the table, it doesn't give you a lot of basically depth. It only covers this portion of this top table. All right. So N equals to 1 here. And by the way, this should be plus or minus. So then N equals plus or minus 2. And then N equals 2MF plus or minus 1. Sorry, actually doesn't give me this. It only gives us this, this, and this. Okay? All right, so we have these two tables. Please, you choose them wisely. And we have an example over here. By the way, the table that you see over here, I've actually, in my handwritten, is basically the same as this table. They are not really different. And so here's our example. Let me make this a little larger. Okay. Before we get to the example, are there any questions? Okay, so no questions. All right. So the example is we have this three-phase PWM inverter, and we are doing bipolar stuff, but I haven't really even mentioned that, bipolar switching. And we are trying to find the total harmonic distortion of the line-to-line voltages. Okay. So line-to-line voltage, table gives me line-to-line. Three-phase, the table gives me three-phase. Bipolar, the table is based on a bipolar switching scheme. So everything is suggesting that I should be able to use these tables. Now, what is the value of MF? It's 15. It's an odd number. It's relatively large, and it's a multiple of 3, so it satisfies our conditions. And MA, the amplitude modulation index is 0.8. The suggestion is if I use this table, I should use these numbers, which are all RMS values, or I can use these numbers in terms of amplitude values. It doesn't really matter which one you use, because in this particular case, they all cancel out each other, the square root of 2's. All right, so looking at that table, so the numbers that you see, let me make it again smaller. So the table is suggesting me that in terms of peak, or maybe these are RMS, let me check. Yeah, in terms of peak. So actually I'm getting these numbers from here. So you can see this 0.693. This is the peak value or the amplitude value of your fundamental harmonic of the line-to-line voltage. So actually I'm using this number over here. And remember, these are all normalized by Vn, so Vn also appears here, but no worries, the Vn also cancels out. And then I have a harmonic at MF plus or minus 2, which would be 15 plus or minus 2, so 13 and 17. So I have harmonics at 13 and 17, line-to-line voltages, and the amplitude is 0.19, which is this number now. Okay. Then let's say we are just using this table 8.8, and then I have harmonics at 2mf plus or minus 1, which gives me 29th and 31st harmonics. 29th and 31st, and the number is 0.272. So that's where this number comes from. All right. So assuming that you are using table 8.8, you don't have to worry about other harmonics because nothing is really provided beyond that. And then going back to the total harmonic distortion was in the denominator you have the desired signal, which is V1. Line to line, and also RMS value. It doesn't really matter at this point if you're doing RMS or not, because as I said, they cancel out each other, but I'm doing it, so that's why I'm actually dividing everything by the square root of 2, because all of these values are amplitude values. I have to divide them to get the RMS values. So that's what it is. And then over here I have the undesired harmonics, like this is giving me the V13 line to line RMS plus V17 line to line RMS. And because they are exactly the same, I've just written it once and then multiplied that by 2 because they are the same, identical. And again, this term is taking care of the harmonics that I have on n equals to 29 and 31. And in the end, it turns out that your total harmonic distortion is about 68%, and it's not actually a good number, which is a good actually point over here that total harmonic distortion by itself is not really a good indicator of how good your signal is. The other factor that you have to pay attention to is at what frequencies do these harmonics appear. Now the good news over here is the undesired harmonics are at very, very high frequency. So I have this fundamental harmonic here, and then the first bothering harmonic is at 13. So I can easily filter this thing out. So you can see if you use PWM switching scheme, your total harmonic distortion gets larger. So here, compare this, 68%, compared to the case that we had last time. We were using a square shape switching scheme. So bipolar in this sense is actually making things worse because your total harmonic distortion grows, which is a bad thing. However, these undesired harmonics are all pushed to higher frequencies, so it's easier to filter them out. And that what happens, your current is much actually nicer and closer to a sinusoidal signal compared to the square shape waveforms. And you can actually look at them here. See this current over here, this curve that we had is almost sinusoidal compared to what we have over here, which is really not. Let me see, where did we have that? This one, which is not really sinusoidal. Okay. So remember, total harmonic distortion by itself may not give you the good numbers or good idea. You should also look at where these harmonics appear. You may have a very significant harmonic at very high frequencies, but no problem. You can easily eliminate that with a simple low-pass filter. All right, any questions? All right. So in case in our quiz we need a table, I will actually provide you the tables. You don't really have to bring it with you or anything. I just give you the table, or actually post it on the board here so you can use it. Now we have some simulations. Here it is. And I just wanted to show you how it works. It's a MATLAB-based simulation. It's not Plex. And in MATLAB, at least at the time Plex was not around, I was very hesitant in terms of using, MOSFETs and things like that. So I'm actually, you can see, this is a this is a power converter, but you don't really see any switches or diodes in it. Okay. So what's happening is, this is my leg A basically. This switch is that single pole double throw switch which behaves those pair of switches of S1 and S4. And this is leg B and this is leg C. And how do I make the decision of should I be in the top throw or the bottom throw? I'm making those decisions based on these signals, this signal and this signal and this signal, which come out of these three adding blocks. As it turns out, these are not really adding blocks. They're kind of subtracting things, but actually they are comparing things. What are they comparing? They are comparing three sinusoidal signals that are 120 degrees out of phase from each other with a triangular waveform. So we are actually making a comparison here, see if this is positive or negative, or which one is larger, and turn these switches, go to the top throw or bottom throw. And this is my DC source, 100 volts. So if I'm choosing the top throw, I'm providing a short circuit path to the 100 volt source that I have. And if I choose the bottom throw, I just choose the ground. Okay, so it's kind of your power stage, even though you're not really having any semiconductor devices. Then, for instance, when it comes to building up your VAN, remember we had an equation here. VAN is twice this voltage minus this voltage minus this voltage over 3. I'm doing the same thing here. Twice this voltage minus this voltage minus this voltage divided by 3. So this gives me VAN. Okay. So if you do all this math, you will get a waveform like this. So let me just zoom in a little bit. All right, it's a little bit busy over here, but as you can see, we have three reference signals, three sinusoidal signals compared against the triangular waveform. And I think the red one was phase A, and then the purple one is phase B, and the kind of bluish one is phase C. These three graphs that I have underneath, this one, and this one, these three basically traces are VA and VB and VC with respect to the neutral point. So you can see they are either 0 or 100. Okay, and the trend is VB is 120 degrees behind VA. Now if I subtract these two from each other, for instance subtract VA and VB, I'll get VAB, which is here, and then I can use that equation of VA, twice VA minus VB minus VC over 3, which gives me VAN, which is this bottom trace number 1, 2, 3, 4, 5, 6. Trace number 6 is VAN. And the last one is actually VN, which is the neutral point of your load with respect to the ground. Again, we are highlighting over here that this is not exactly 0. Let me zoom out a little bit. And actually, I have a better one here. Okay, so this is actually our VAN, line to neutral voltage for phase A. So remember, it settles either at 2VN over 3, which is 200 over 3, which is 66, or VN, I'm sorry, and or VN over 3. VN is 100 over 3, 33. So this level is actually 33. So if you really zoom in, you can see it's almost a sinusoidal signal. Again, it's not exactly sinusoidal, but you can argue that there is a significant AC harmonic in this signal. So this is actually your line to neutral voltage. I don't know if this file is on Blackboard already. If it is not, I'm going to actually post it there, but you can easily spend a little bit of time and do it yourself, maybe in Plex. Might be a little bit easier to understand because here we are doing a lot of math. If you make a mistake, everything is actually going to give you a wrong value. Let me see if there's anything important over here to highlight. Yes, and that is, again, please remember the bottom trace over here is your line to neutral voltage, which is actually, I'm sorry, neutral to ground voltage, so it's never zero. It's always fluctuating from some point to the other. All right, any questions? Okay, so let's go back to this presentation by the author of this book. See if there's anything that the book discusses that we haven't discussed. Yeah, again, these are three-phase multi-level inverters. So technically, if you look at this point, we are not going to cover this in details, but anyway, this is again A, B, and C. And if you look at the voltage of point A, before it was either 0 or VDC. Here, VA could be VDC, and that is when you turn this switch on and this switch on. So VA is actually shorted to your source. Or VA could be VDC over 2, which is the voltage of this cap. And how does that happen? That is when this diode is turned on and this switch is on. Or it could be 0. And how does that happen? And that is when we have a short circuit path here and here, for instance, through the diode. So now you can acquire 3 levels for your A to ground. Before we couldn't actually create this one. So now that you have more levels, that the indication is the resolution of your output voltage is going to be better and total harmonic distortion is going to be better. But I don't really see any results over here. Then the book talks a little bit about what we talked last time, that a lot of times when you have an inverter, that the indication is you do not really have a DC source. You have rectified an AC source to get a DC source, or a DC cap voltage kind of a thing, a link DC voltage, and then you invert it back. So this is an example of a 3-phase variable speed motor drive. Your source is a constant frequency, constant amplitude AC source. You rectify that. And again, in this rectification, you can use controlled rectifier. Like instead of diodes, here we are using these SCRs. So by controlling the firing angle of these SCRs, I can have a variable DC link over here. Like this is how most of power supplies work when you go to the lab and do experiments. Actually, that's how it is. And then on the output side, I have again this 3-phase inverter, which is like 6 IGBTs or 6 power MOSFETs with the associated diodes. And then I can control, for instance, the amplitude of the voltage that I'm generating from, for instance, if you call it, well, first of all, this diagram has a problem, and that is this should be grounded here probably. This not supposed to be here. Okay, so let's call it A. And there is a neutral point here. So VAN could have a high amplitude or low amplitude, and therefore you can adjust the power that is being supplied to the electric motor, or ultimately you can adjust the speed of the electric motor. This could be, for instance, a large air conditioning unit, or something like that. Or in a factory you have a motor that is pulling things, and you want to control the speed of that electric motor or something like that. All right, so this is pretty much the end of chapter 8, all about inverters. Everything we have covered in this chapter will be covered in the quiz on Tuesday. Now we are going to move on to a new chapter, chapter 9. And this chapter is all about soft switching schemes. Okay, or resonant converters, so soft switching. Okay, so as it turns out, all of the switching schemes that we have talked about so far, like for a boost, buck, those kind of converters, they can be classified as hard switching schemes. And now what we are going to cover in this chapter is kind of a new way of doing things, which is called soft switching, and we are going to see why one of them is called hard, the other one is called soft. But we're kind of going back to the very basic topology that we analyzed earlier in this class, which is the buck converter here. So here we have this buck converter. All right. And we want to focus on, for instance, the switch in this converter. Like, we are monitoring the voltage drop across the switch and the current of the switch. All right. So if this is an ideal converter, when the switch is on in mode 1, remember, this is an ideal switch. So you don't see any voltage drop on the switch. So it's like a short circuit, 0 voltage. And the current is kind of, remember, the current is kind of rising. But over here, we don't really care about the rise of this current. We only care about the value of this current at the end. So technically, what we do is we can argue that I don't really care. I know that this current is just non-zero, okay? Then the switch turns off when mode 1 ends, and that means the diode is going to be on, and the voltage drop across the switch is Vn, and the current instantly goes to 0. Okay? Make it a little larger. All right. So ideally, this is what's happening in the system. Switch is on, voltage 0, current non-zero. Switch is off, current 0, voltage non-zero. But in the end, if you are focusing on this switch as a component in the system and you want to see how much power is being lost or delivered to the switch, what you do is remember, instantaneous value of the power was the instantaneous value of the voltage multiplied by the instantaneous value of the current. So you have the voltage waveform and the current waveform of this particular element. You just multiply them by each other to get the power. Now, as it turns out, because voltage is 0, current is not 0, or current is 0, voltage is not 0, when you multiply them by each other, you just get 0. What does that indicate? The indication is, ideally, you're not really losing any power in this switch. Okay, this switch is 100% efficient. All right. So this is the ideal case. What happens in a real case? Here is what happens in a real case. In a real case, basically what happens is these transitions are not ideal and they are not instant. It takes a little bit of time for the, for instance, current of the switch to come from whatever non-zero value that it had to come down to 0. Or it takes a little bit of time for the voltage of this switch at turn off to rise from 0 to the ultimate value of Vn. So now we are kind of magnifying things. This is really not taking this long, but we are kind of exaggerating things. So it takes a little bit of time here. So the switch was on here during mode 1. No voltage drop on the switch. Again, so far, from that perspective, the switch is ideal. Doesn't have any internal resistance. Because we are not focusing on the conduction losses of the switch, we are only focusing on the switching losses of the switch. Then when you turn the switch off, it is trying to get to Vn, but it takes a little bit of time. Okay? Now when you're turning the switch off at the same time, if you focus on the current is non-zero up to the point that the voltage has gone to the high value and then comes down. All right? And the same thing happens when you're turning the switch on again. There's a little bit of transition here, there's a little bit of transition here. So ideally, if you really zoom in, again, zoom in, and you're kind of exaggerating, this time doesn't really have, this is not a very long time. It's like maybe, I don't know, 10 nanoseconds or so, or 15 or 20 nanoseconds. But anyway, now you can see that in reality, there is a little bit of an overlap between the current of the switch and the voltage of the switch. So now if you multiply them by each other to get the instantaneous value of your power, so in this area, voltage is 0, so I get 0. In this area, current is 0, so I get 0. But during the transients, I get something that is not 0. All right. So now you can argue that in reality, you're losing a little of energy or power every time that you turn your switch off or every time that you turn your switch on. So these are called switching losses. They are associated with these switching transients in the system. Now, what exactly is it going on? Is it really like what I drew over here or not? The answer is no, it is not. It depends on what kind of switch you are using, who is the manufacturer of the switch, do the manufacturers do they even provide the details about this? They don't really honestly do that. But you just know that deep down there is a little bit of an overlap. So it could be a case like this, for instance. The voltage goes up, and at the very same time the current comes down. So now if you multiply them, let me draw them here. So I need a third trace. Okay, so there could be a case like this. So now if you multiply them, it's 0 before, it's 0 after, but non-zero during this transient. Okay? So the point is there is some overlap, but how exactly does this overlap look like? What exactly is how exactly is the voltage rising, or how exactly is the current falling during the turn off? As I said, depends on the manufacturer of the switch. Have they made these measurements? Are they reporting these measurements or not? So it's not always, your power is not always triangular. It could be like a second order kind of a thing, or it could be something even weird looking. But it's non-zero, that's the whole point. All right, so one graph, this graph comes from Dr. Mohan's book. It's kind of popular. I don't honestly know how accurate it is or not, but the whole concept is, if I plot the voltage of the switch and the current of the switch versus each other, okay? When the switch is off and the transient is over, we are here. That means you have some voltage drop on your switch, but the current is 0. So what is this indicating? This is, for instance, indicating a point like here, this. When the switch is on and the transient is over, you have some non-zero current passing through the switch, but the voltage is 0, which is indicating a point like this. Now, when you want to go from one point to the other, then you're going to take a trajectory like this. For instance, this is for turning the switch on, or a trajectory like this when the switch is turning off. Now, I honestly don't know how accurate these trajectories are, because you may come and say, no, it doesn't look like this, it looks like this, something like this. And I can't really argue for or against you. It depends on what switch you're using, what the dynamics is, how the switch is built, those things like that. But it's kind of commonly accepted that something fishy is going on, and we have like a square shape, a square over here, almost a square. You can see it's almost a square. And the area underneath this square is kind of representing your losses in the systems, the switching losses. Okay. Yes?
Like, voltage across the switch, you're turning on the switch at time t.
Okay.
Why is it like the voltage extending from t to...
You mean here?
Yeah.
Again, that's the matter of debate. Is it really happening like this? So the question is, how come we turn the switch off here, on here, but the voltage remained at a positive value, okay? Some people argue that first the current has to rise to where it is supposed to get, then the voltage starts falling. Okay, then again I can argue that no, that's not necessarily true for all switches. But this would be the worst case scenario, that you are trying to turn the switch on, the voltage doesn't go to 0, doesn't even start going to 0 until your current has reached a certain value. Okay, so that's what's happening. Again, it may not be exactly true. Okay, it could be, I don't know, something like could be something like this, and this could be something like that. Again, I don't know. Other questions? So now we see that in reality, every time that you turn the switch on and off, you lose a little bit of energy, which is called the switching losses. So that's actually one of the kind of impeding factors to go to higher switching frequencies. So the higher the switching frequency, the higher the losses are. And therefore, on one side, you have, for instance, a smaller inductor and a smaller cap. But on the other side, your losses are higher. Therefore, you have to use a larger heat sinks. So kind of there is a trade-off there. All right. So if this is the case, are there ways of reducing these switching losses? And the answer is yes. And how do you do that is by manipulating the system in a way that you turn the switch on and off during the time that either its voltage is 0 or its current is 0. So there are two main categories here. It's called ZVS, or zero voltage switching, or ZCS, zero current switching. Okay? So ZVS, ZCS, they are both considered soft switching. So this is called a hard switching scheme, and or again, this is still called hard switching scheme. But if you manage to do it in a way that, okay, you still have the off position here or on position here, but if you manage, for instance, you're trying to turn the switch on, your voltage, instead of going this way, if you manage it to go this way, then you can argue that the area underneath this curve is reduced, therefore your switching losses are reduced. Or during the turn on, the same thing. All right, something like that. So that's why it's called a soft switching, doing things soft in a way that, for instance, let me draw it over here. So, for instance, if you focus on voltage of the switch, and then the current of the switch. So let's say this is going on, our switch is on, and you want to turn it off, but you want to do it with a ZVS kind of a thing, meaning that the voltage of this switch has no hurry to go to that ultimate V-in value. It actually, for instance, there's a capacitor in parallel with this switch. So instead of trying to jump to that final value, it gradually rises. Okay? So this would be hard. This would be soft. So in this case, even though there is an overlap, between these two, because this value is very small to begin with, so it's when it's multiplied by something else, it gives you a small value, so you can argue that your switching losses is reduced. So you can have topologies, and we're going to actually look at some of these topologies that provide zero voltage switching at turn on, or maybe during turn off, or maybe during both. And then we have topologies that provide zero current switching at turn on or off, or maybe both. Now the argument that we made here is also true for diodes. So there might be a particular topology that provides, for instance, ZVS for a particular switch during turn on, and it provides ZVS for a particular diode in the circuit during turn off, those kind of things. So I mean, when it comes to ZVS and ZCS, you have to focus on each individual particular switch and argue, is there a ZVS here, is there a ZCS here, what's going on? All right, so there is a kind of a classification of these converters. I don't honestly know how valid this classification is. One category is called resonant switch converters. That means you are adding some some capacitor, so like a very small cap or a very small inductor around your switches and diodes to provide this ZVS or ZCS conditions. So they're called resonant switch. The switch is contributing in some sort of a resonant circuit. Then there's a category called load resonant converters. That means you are providing this resonant circuit somewhere else, which is around your load, like a resistor, like a capacitor or an inductor. And there's a third category, it's called resonant DC link converters. That means the DC link that you have, for instance, we had a DC link voltage over here. Okay. We had this. We have this DC link over here. Okay, and the voltage of this DC link is almost constant, DC constant. But somehow, if you manipulate the system and say, okay, this voltage is sometimes going down and then coming down, and then when this voltage is zero, you do a lot of switching, everything is zero at that point, so you actually have minimized your switching losses. So this is called resonant DC link switching schemes. Okay. So there are, okay, maybe thousands, if not tens of thousands of different approaches of doing that. This concept of soft switching started in like late 70s. It was a hot topic back in the 80s and 90s. It's a little bit of a hot topic, but later we are going to see you're trying to solve a problem at one point, then you're going to add more problems somewhere else, and we're going to see that in the analysis that we are going to make. So there are ZVS and ZCS solutions that are very, very popular, but there are tens of thousands of other papers published in this area that are not necessarily very popular. But I mean, it's a kind of a math-based kind of approach. You can do a lot of fun stuff, at least on paper. All right. So as it turns out, what we do in order to achieve this ZVS and ZCS, what we do is we add a little bit of a cap, for instance, in parallel with our diode or with our switch. Or we add a little bit of an inductor and place that in series with our switch, those kind of things. So to create some sort of a resonance behavior in the system. So as soon as this term resonance comes in, what we should do is we should prepare ourselves for analyzing resonant circuits, okay? And I believe this is not in your textbook. This comes from the Dr. Mohan's book, but anyway, I've actually listed them over here as basic topologies or basic resonance topologies or basic concepts, all right? So in analyzing a soft switching or a resonant converter, sometimes you find yourself with this circuit, that you have a DC source, or it could be a very large capacitor, and then you have a resonating small inductor and a resonating small capacitor placed in a loop. So this is like kind of a circuit one kind of a thing. So, and also we have the initial conditions available. The initial value of the inductor current at the time that the configuration happened like this, formed like this, was IL0, and the initial value of the cap voltage was VC0. So at t equals to T0, all of a sudden, for instance, you had a switch somewhere or something happened, now you have this topology created. Now you have to be able to analyze it. So going back to circuits 1, there are two differential equations. One of them is this KVL around the loop, which tells me the voltage drop across the inductor plus the voltage drop across the cap should be the same as the input voltage. And the second equation tells me that the current of the cap is the value of the cap times the derivation of its voltage. So we have two independent differential equations. Going back to circuits 1, if you do the math, you are going to end up having an answer like this. So equation number 1 is telling us what happens to the current of the inductor. Equation number 2 tells us what happens to the voltage of that cap. And this is IL0, the initial value of the inductor current. And this is VDC, our DC value of the source. And this is VC0, the initial value of the cap voltage at the beginning of this study. The beginning means T0. And same here. VDC is the DC value of the source. Again, VDC here minus VC naught, and this is IL naught, the initial value of the inductor current. Okay. So technically, if you look at this, you see there is lots of resonance going on. And by the way, omega naught is defined to be 1 over the resonance frequency between the resonating inductor and the resonating capacitor. The resonating inductor was called LR, resonating inductor, and CR is the resonating capacitor. And omega naught is 1 over the square root of these two multiplied by each other. And then Z naught, which is called the characteristic impedance, which is the square root of LR over CR. So we define these two basically parameters. For instance, Z naught appears here. Z naught appears here as well. And please remember, Z naught is not a complex number anymore. Z naught is just the magnitude of actually that impedance. So it's not a complex variable. All right, so this is one case. I'm hesitant about drawing these waveforms for you. But if you think about it, the current of the inductor starts resonating, and the DC value of this signal is still 0. Remember, most of the times when the current of an inductor is periodic, the DC on average, the DC value should be 0. So if you look at this, okay, we started with like IL naught. So this is I of LR, and it kind of resonates around. I'm very hesitant about drawing it because I might be wrong, but something like this. And then if you look at the voltage of the cap, it resonates with the DC value of your input voltage. So it resonates around this level of VDC. Something like this, okay? So there is some resonance going on. Now, we have two other examples of these circuit parameters, and as it turns out, one of them is actually like, we can only use, let me see. This is the most complete one. So the case that we just studied was this topology without having any DC current over here. So if you get this DC current source out, you will be reduced to basically case number 1. This is case number 2, and we are going to analyze it next time. Again, you have a resonating circuit in which there is a DC source, which is either your really DC source or a very large cap. Then we have a resonating inductor, a resonating capacitor, and also a DC source, DC current source over here, which is actually the main inductor in the system because it's a very large inductor compared to the resonating components. So it behaves more like a DC current source. And then there's a third case, which is, I guess, a special case of this, and that is basically case number 3 over here, which is when this DC source does not exist and it's more like a short circuit. So if you just focus on case 1 and have the equations associated with case 1, cases 1 and 3 are special cases for case, if you have everything about case 2, cases 1 and 3 are special cases for case 2. So we're going to start looking at these and then go and start analyzing our first resonating converter, which is basically this topology. As you can see, it is this Buck topology. So we have one switch, one diode, the inductor is over here, the cap is over here, but in addition to the components that we have seen before, now we are using a little bit of a resonating inductor here and a little bit of a resonating capacitor over here. So by adding these two components, things are going to get way complicated, but we are going to achieve, for instance, the ZCS, the zero current switching that we wanted to achieve. All right. So see you guys next week on Tuesday, and don't forget about your quiz.